Hello everyone, welcome back to PTED Chemistry channel. My name is Dr. Ott. In this tutorial video, we'll go through this topical series for AQA A-level chemistry. This is specifically on isomerism. This is isomers for the organic chemistry syllabus. So in this first question, each of these parts below concerns a different pair of isomers. So this exists as a pair of isomers here. So draw one possible structure. When they say draw one possible structure, they did not mention display, they did not mention structural, they did not mention skeletal. So whenever possible, I usually will go for skeletal because skeletal formula is simple, it's elegant, and it's quite easy to draw and quite fast as well. So compounds A and B have this molecular formula C5H10. Molecular formula is the actual number of atoms present in one single molecule. What are some of the characteristic reactions or properties we are given here? Decolorizes bromine water, so that means there is the presence of carbon-carbon double bond. This is called unsaturation. We also could see from the general formula CnH2n. This is what we associated with a straight chain alkene most of the time from your IGCSE or O-level chemistry. But here, even though you are C5H10, B does not decolorize bromine water, so no unsaturation there. So in terms of A, one possible structure, if you want, you can draw the straight chain, but you can also draw an isomer of it. So carbon form 4 covalent bond, but I think we do have a double bond there. So you could do the double bond at position 1 or at position 2. That will give you different isomers, as you have learned about position isomers. Carbon form 4 covalent bond, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So here there are 2 already, so I just need to put in the extra 2 hydrogen. 2 hydrogen, 4, well, 2, 3, 4, 5, 6, 7, 8, 9, 10, C5H10. So that is for A. You could, of course, draw other possible isomers that contain alkenes that will be entirely correct as well. You could also draw the skeletal formula that will be entirely correct if you do them properly. As for the alkanes, well, alkanes but not CnH2n plus 2 is because you have a cyclic structure. So I'll show you when you have a cycloalkane, carbon form 4 covalent bond. So each of these carbon will just be CH2, and that is why you have C5H10 without the carbon-carbon double bond. This is called cyclopentane. A 5 carbon membered ring alkane. So this is isomer number B there. In part B, compounds C and D have this molecular formula C2H4O2. Each of them had an absorption in infrared. So this infrared absorption is indicative of a carbon-oxygen double bond. This is a carbonyl. As for what functional group it is, I can't tell you yet, but definitely contains C double bond or bond. Only D has a broad absorption. Key there is a broad absorption, and this is around 3000 to 3500. This is indicative of D, but then C has no OH. Okay, so when we look at these C2H4O2, I'm thinking about carboxylic acid because there is 2 oxygen. I'm also thinking about ester because carboxylic acid and ester are in the same topic simply because they are functional group isomers. If you draw out carboxylic acid and esters for the same number of carbons, you will be able to show, just like for this question, they are going to be functional group isomers. These are under the umbrella of structural isomers. So let me try and draw this for you. Let me see. In C, what we have is going to be C double bond or OH. Oops, sorry. Only D has OH. So this one has got to be an ester. C double bond O and then OH. And then C H3 CO2H. So there are 2 carbon. There are 2 carbons, 1, 2, 3, 4 hydrogens and 2 oxygen there. So that has got to be D. That has got to be D there because D has got carboxylic acid. Whereas the ester I'm talking about C double bond or O. However, we know that when we form ester, the carboxylic acid will have lost the OH, and then the alcohol will have lost the H. So this is going to be 1 carbon from the alcohol, methyl, and then this is 1 carbon on the acid. Therefore, you're left with just 1 hydrogen. this was from methanoic acid, so you will get methanoate as the name of the ester. And then the pink color one from alcohol, from one carbon alcohol, you're going to get methyl methanoate. Be careful, carbon from 4 covalent bond, 1, 2, 3, 4. This carbon is fine. This carbon was from the alcohol component. You got to draw the remaining bit of the alcohol there. That is going to be, which one is that? That one is C then, because that one contains ester. Without it being carboxylic acid, there is no OH bond in C here. So ester and carboxylic acid, they are functional group isomers. Same molecular formula, C2H4O2. Different structural formula. I've drawn display there. If you have drawn skeletal, it will have been correct as well. Part C, so specifically we are told that both of them are esters. So esters basically contain C double bond or O like that. And it cannot be hydrogen at the end. It's got to be a carbon-based group. This is about proton NMR. So if you are doing AS/AQA chemistry, forget about this. So proton NMR is about A2 organic in the AQA syllabus. So you can forget about this. If you are doing AS, you just move on to the next question. However, if you are doing A-level chemistry, and this is a recap of your AS, then this is going to be useful. So we got 2 singlets only. So we got 5 carbon, but we have 2 singlets only. So this indicates that it's a symmetrical structure. Because you got 5 carbon, you expect to have 5 different, you have your proton NMR, you got 10 protons, you expect to have different environment for the protons. So this must be symmetrical to only have 2 singlet, symmetrical environment. Whereas you can see F is a bit more complicated. Whenever we get a quartet and a triplet, so a quartet is 1:3:3:1 splitting, and triplet is 1:2:1 splitting. So a quartet and a triplet typically together, they indicate a CH2 and a CH3 usually. But you have 2 sets of it, so indicative that you have 2 sets of two times different CH2, CH3 there. So I think I'll go for F first because F is a bit less symmetrical because you have 2 different quartet and 2 different triplets. There are 4 different environments altogether. So there are 4 different environments, 4 different proton environments in F. So that means we don't really have much symmetry. So that means almost everything is unsymmetrical, almost everything is not the same. So I could imagine this as C double bond O, and then you can imagine this being your CH2, your CH3, and then you got another CH2, another CH3. So I've drawn a partial structural there. They just asked us to draw. So you can see that this side belongs to the carboxylic acid end, and this side belongs to the alcohol end. These are ester, these are ethyl propanoate from the propanoic acid. So these are, when you are here, let me just show you. They don't ask you to explain, of course. When you are here, the first one, you will have 3 different protons. 3 of the same protons, but you see 2 neighboring protons. So therefore, this will get a triplet. When you're on the next one, you will have 2 protons where you are. You see 3 neighboring protons. Therefore, 3 plus 1 give you 4 lines. You see a quartet. And the CH2 on the other side, again, 3 neighboring protons. This is a different quartet now because it's not the same environment as that. It's going to be quite similar, but it's going to be slightly different then. And the last one there, triplet, you get 4 different environments, according to the question there, okay? And as for E is going to be quite symmetrical. So there are 2 singlets only. So I can imagine this being C double bond O. So the only possibility when it's quite simple looking is if it is something like this. You can see 1, 2, 3, 4, 5. But they are esters. Okay, so if they are here 1, 2, 3, 4, 5, then this must be hydrogen, and we know that it's ester. So this CH3, these are tertiary group. The carbon there bonded to 3 different carbons, 3 other carbons, cannot be on the carboxylic acid end. So perhaps that is not true on the C double bond O. Perhaps that is true on the alcohol end. Then what happened on the other side is you will just have C double bond O, and this must be from methanoic acid. And I am allowed to put H there because there is such a thing called HCOOH. The carboxylic acid lost the OH, the alcohol lost the H, and then you get these ester 1, 2, 3, 4, 5. These three are going to be the same environment. They just give you a single singlet. This is just one proton there. There's another singlet there, and therefore you get two different singlets, and very symmetrical, very, very simple looking NMR there. Part D, compound G and H. So this is again back to AS type of reactions, or maybe not. I mean, there's optical activity there. So that means you have chiral center, a chiral center or a chiral carbon, a carbon bonded to 4 different groups there. So H does not. But look at C3H6. That is very funny looking because there is Cl. Is that Cl2? I think this should be Cl2. This must be a typo there. C3H6Cl2. So there's 2 chlorine there. And we're looking at 1, 2, 3. So the usual thing CnH2n plus 2 will give me C3H8. I must have replaced 2 of the hydrogen with the chlorine. And we're looking at, let's say, chlorine, hydrogen, and what else? CH3. And then a CH3, is it? So this looks like, oh no, that doesn't look like it. So perhaps I can have, let me just draw the chlorine by using a different color so that it's quite obvious. So chlorine and chlorine. So chlorines are on different carbons. I can see that I have a chiral center there because I mark it with asterisk. This carbon is bonded to the right hand side that has got chlorine, the left hand side that has got no chlorine. So the left and the right are different groups. Hydrogen and chlorine are different groups. This carbon has got 4 different groups attached on it. So it's a chiral center. So this must be G. And you can draw the mirror images by drawing in 3 dimensions. So draw 3-dimensional tetrahedral geometry and show the mirror images. Those are usually a few marks, well, 1 or 2 marks in exam questions when they ask you to draw the non-superimposable mirror images of each other. So H must be the one without the chiral center. So without the chiral center, I can imagine where I can put the chlorine. If I put the chlorine on the same carbon, so that means this must be hydrogen there. So the left and the right are exactly the same. Then I put the chlorine on the same carbon. Again, C3, H6, Cl2. But this carbon now has left and right group the same, top and bottom group the same. So no chiral center for H there. Therefore, not optically active or no chiral center. Therefore, you cannot rotate plane polarized light in opposite direction there. Compound E, the last bit of this question, again, okay, this is about infrared. So infrared is AS in AQA chemistry, but then the proton NMR spectrum is in the A2 AQA, meaning to say A-level syllabus. So you might not be able to do this unless you have finished your A-level analytical chemistry. So here we get a triplet and a quartet. So these are indicative of a CH2-CH3 ethyl fragment. But you also have a singlet, so maybe we are looking at something else now. So this is C6H12, C6H12, CnH2n, indicative of an alkene, carbon-carbon double bond, but it could also be a cycloalkane, where we saw earlier, you could have a cyclic ring, a cyclic compound with no carbon-carbon double bond. We have at about 1650, so if I'm not mistaken, this is indicative of a carbon-carbon double bond. Each one has absorption, so each one is an alkene, and none of them shows geometrical isomerism. So there is no E and Z, no E or Z isomers. Okay, so proton NMR of I consists of a singlet only. So what we are saying is it's very symmetrical for compound I. So we have 6 carbon. All of the carbon are exactly the same. So I am thinking about something that looks like this, C6H12. So what we have is just a regular hexagon where we have CH2, 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 like that. Because all the protons are exactly the same, you get a singlet. But that is C6H12, so that doesn't make sense. Okay, maybe the 1650 is not carbon-carbon double bond because this is the only way you can get a singlet only where all the protons are exactly the same there. Let me just double check my infrared spectrum. So it cannot be carbonyl. Where is my infrared spectrum? Yeah. Just give me a minute. Let me just find my infrared. Okay. So it's not a carbonyl because there is no oxygen there. Yeah, I mean that is looking at carbon-carbon double bond, to be honest. Alkenes. So it's got to be alkenes there. It's got to be alkenes. So maybe this is wrong. So this cannot be the answer. Cannot be the answer because, you know, no carbon-carbon double bond, whereas this 1650 refer to carbon-carbon double bond. So what else are we looking at? So maybe we are looking at something like this. So CH3, 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 and CH3, because they are totally symmetrical and there is no proton there. So this and this and this and this, there's a mirror plane there and a mirror plane there. There is 6 carbon, and then 3 times 4, there's 12 hydrogen. So this one must be I, is it? No, yeah, I, because I is the one with the symmetrical NMR spectrum. Then how about the next one? We definitely have carbon-carbon double bond. We have a triplet and a quartet. So a CH3, a CH2, and then this might be bonded to a carbon double bond like this. And what else do we know? We know that there's only a triplet and a quartet, so they must be symmetrical. So there is no cis and trans. When I say cis and trans, I mean E and Z. If I draw the CH2, CH3, so this one can have E and Z. These are on opposite sides, and none of the two groups on the same carbon of the double bond are exactly the same. So you can have E and Z here, but this cannot be our answer. There is no E and Z for either of the compounds. So instead of doing that, what I could do is I could move and have a CH2 or CH3 on the same side. That means there must be hydrogen on the other side. So what do I have? I have a singlet. So these two are exactly identical. So this is my singlet. So the CH2 and the CH2 there is identical. They will see 3 neighboring protons, and therefore when you are here on the CH2, you will see a quartet. Because you have 3 neighboring protons, 3 plus 1 give you 4 lines. And last but not least, when you are at the terminal CH3 and CH3, you will see 2 neighboring protons, 2 plus 1 give you 3 lines. So you get a triplet, a quartet, and a singlet there. And it must be like this because when you have CH2 terminal alkene, there can be no E and Z because these two groups are exactly the same there. So yes, this is a 10 marks identification of the structures, but I've discussed a lot more about analytical techniques, a little bit about NMR, which is A2, AQA stuff. But the earlier bit of the questions, they are all perfectly AS level questions. So I think that's it for this short tutorial video. A little bit on analytical chemistry, but mainly on isomerism there. So thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Do follow me at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected and stay updated with future tutorial videos. And do get in touch with me, Dr. Ond, at 673 for the country code and then 86566158 to arrange your private tutoring where I can go through any concepts, any topics, as well as any questions of your choice. Thank you for watching again. I'll see you in the next tutorial video.